Yeah. Okay. Are we looking good? Great. Okay. So we're going to start, even though Brian's not here, but so we're going to talk about the package SymPy. This is a package for Python that is used for symbolic mathematics. Symbolic mathematics is defined as a branch of computational math where we don't actually solve things numerically or with numbers, but solve for expressions. So how you might do an indefinite integral, you apply those algorithms in your head when you know that this integral equals this, and the same thing goes for your computer. So the syllabus is as follows. We're not going to say all those words, but if you want to look at it before we get into it, we'll start with an introduction. So symbolic computation allows for these exact representations of mathematical expressions. So when you type square root of 2 into your calculator, your output is going to be something like 1.1, 1.4, something like that. But when you do this symbolically, you're expected to have a square root unapplied to your operator or to your number 2. So we're going to import these packages specifically. The last one is just so my stuff looks a bit swanky. You can ignore this. But let's import all these packages. We'll run them when we do our code. Right. So regardless of if you're done or not, we'll go a bit over it. So we'll do what a calculator does. We'll just compute the square root of 2. This is the exponential or the power operator. So what this is doing is it's raising 2 to the power of 1/2. The output here is going to be something like we said before, 1.4. However, we're going to talk about how the SymPy package represents this. So we're going to write SymPy.square root of 2, and we're just going to display that. Now that's obviously what we talked about before, where the square root hasn't been applied exactly. And this might come important in some applications. Maybe specifically, we'll look at this. So this is the square root of 8. When you type it in, it's going to give you something very similar to twice your square root of 2, but sometimes you won't be able to notice that. However, when you type that into SymPy, not only is it going to represent it exactly, but it's going to simplify it. So this is something that is going to help a lot when you're doing your mathematics. There are a lot of trig expressions that need simplifying. There is a lot of stuff that we take for granted and that we could do better with computers, I guess. So SymPy factors out all of these simplifications, but only the ones it deems optimal. So some simplifications aren't quite simpler. They're a matter of subjectiveness. So we'll do the main thing that we start with when we work with SymPy. We'll create these symbols objects. X. So this is defining an object X and an object Y to the symbols X, Y. So when we print these, I think that symbol is defined. Oh, whenever we refer to the package, we're going to do SymPy dot. That's the start of everything. Later on, we'll do a shortcut over here. But for now, we're just going to show you how these look. So whenever you just type an expression that you defined before, it's just going to print it out. So we'll define something like fxy is equal to x squared minus y squared plus 1. And we're going to print it out. The expression is going to come out exactly because we haven't input any numbers yet. So one thing that we have to keep in mind is how SymPy does simplifications. In general, it does them automatically, but as we mentioned before, it's a bit subjective. So if we multiply this by x, SymPy won't apply this x to every element, even though some people might consider that simpler depending on the situation. Oh, and just let me know if I'm going too fast. We're just kind of bouncing off of everything right now. So we'll define another expression. fxy2 is equal to SymPy dot expand fxy times x. And we'll display this as we've done before. Now that we've done, we use the expand function, it actually applies this element x that we multiplied it by before to every single term here. Similarly, we can take this fxy2. Someone knocking on the door? We can take this fxy2 and we can we can factor it. So we can use the factor function over here and just plug in fxy2. And it's going to just, oh, yes, I forget. And it's going to go back to our original expression. So now we'll do a shortcut. When we type this from SymPy import this asterisk, we're taking the superclass and making it the inherent operators that we apply to these objects. So now we're doing the SymPy addition instead of the numerical addition that we've done before. So I have a demo here. Whenever I type in demo, what I want you to do is not type anything. Take it easy. Take a break, because really a lot of these are a lot of things to write, and it's more to show the functionalities of SymPy. So we'll start this demo. We define a symbol x here, and we define an expression. It's a big trig expression. It shouldn't look too structural. There's no simplifications that you can make off the top of your head, I'm guessing. However, when we put it through the simplify, it actually just pops out sine of 6x plus 1. Now that saves a lot of time, maybe 20 minutes of getting something wrong over and over. And that's kind of what we're going for. The next thing here is we're going to define an equality. Sine of x is equal to x, and we're simply going to solve for the values that this fits under. So we have two solutions here, 0 and pi. Pretty simple stuff. SymPy will use the solve function later to solve many simple equations, but it turns out that once you have tougher problems, you have to apply different algorithms that are within the subset of solve. So here we'll define a derivative of x to the x to the x. If we apply this .doIt function or method, it'll just do the derivative and it'll apply it to the whole thing. Now there's no way you could possibly do this by hand unless you're, I don't know, like you spent 2 hours on it. That's a little silly. So we'll go for something else. We'll take this very well-known integral from -infinity to infinity of e to the negative x squared. You could actually possibly do this. The integral of this before you plug in the infinities is the error function. But most people don't know off the top of their head what the error function outputs when you put an x into it. So we'll just do this integral, and it turns out to be something very simple, the square root of pi. Over here, we'll solve a very, it's a simple, depending on how you define it, differential equation. We'll use the dsolve function, and we'll get the solution in terms of non-simplified terms. So we haven't put any initial conditions, but we'll still get a general solution that we can use very simply, or where we can apply the initial bounds. Finally, to show some of the functionalities, we'll define a very simple matrix, 1, 2, 2, 2, and we'll get the eigenvalues over here. We have 3 over 2 minus square root of, you get it, but the multiplicity is 1 for this, and the multiplicity is 1 for this other factor that is the eigenvalue for this matrix. So we got a little deep into the functionalities for SymPy, and we see how it can kind of help us simplify expressions. But we'll look at some basic syntax over here. All right. First things first, something that we should know is what you can do in Jupyter Notebook, sometimes in, can you do this in Google Colab? Like, I'll show you what I'm doing, but if you press tab and you put your SymPy class, your superclass over here, you can look at all of the functions here, and you can choose one at random. And if you ever need it, you can just type a question mark, and it'll give you all of the inputs, what the function does, a bunch of references, etc. So we'll take this input away, and we'll comment this out for now. But the point of this is you don't have to look stuff up on Google. It's all inside of the package that you've already downloaded when you got Anaconda. If you're working on Google Colab, you might have to install the package. Hopefully that's not a problem for anyone as of yet. But we'll go next to. We'll go again on how to specify variables. We'll type x is equal to symbols, x. And we can pass a few more arguments here, like for example, real is equal to true. This might be useful if you're solving an equation that is on a specific domain. But for now, this is just kind of an introduction to it, and we'll see some examples where that can be very important. We'll print this x out as well. So, get this out here. When we define x is equal to 1, and we also pass x plus 1, what we've done is we've defined a new value for x. So if we make an expression, expressions that have been assigned on an object don't change when you change that object. They kind of are stuck in this petrified state where they've used the object in the past. So if we do, for example, expression is equal to x plus 1, and we say x is equal to 2, and we print out the expression, what do you guys think is going to pop out? Any ideas? Well, we'll see. It actually pops out 2. So that's because we've defined x plus 1 here before. And when we've done so, we've made the object be superseded by just a number. So we'll define the object again, x.symbols. We'll get the expression, x plus 1. And I'll teach you a new method. If we put dot subs, we can replace a variable, which is your first input, with any number that you desire. So this got really big. Great. And when you print this out, it's just going to put, it's going to do your expression x plus 1, but it's going to plug in the 2 that you've specified for it. So we'll define a few more variables. X, comma y, comma z is equal to symbols x, y, z. And then we'll do expression is equal to x plus 1 again. But we'll actually sub in something else. We'll do expression.subs. And we'll sub in x for x times y squared times z. And it turns out we don't actually have to use a number when we sub in our functions. We can use any specific value that we want, any expression, any elementary function. And this helps when you're doing a coordinate transformation, for example, and you want your result at the very end when you plug in your numbers. So we'll go here and we'll now make an expression is equal to x squared plus y to the third. And then we'll do expression.subs. And we'll sub in multiple values. So you can make an array here to designate more than one value. You make a parentheses to couple these parameters together. So we sub in x for z cubed, and we'll sub in y for sine of z. We'll close this parentheses, and we'll print this out. And now we've put our equation in terms of one single variable. So this might happen when you have one equation that you can use to eliminate your variables. And this is a very easy way to sub things in. And you can just sub things again. So for example, we can sub z for 1. And then we get just sine cubed of 1. I don't know how much that is, but you get it. We'll teach you a little shortcut. If you press init session over here, or if you type this out, you're going to do your command for SymPy to import the superclass. We'll get 4 different variables over here. We'll get a few symbols that are also defined by integers, and then we'll get a few functions here, and then we'll initialize printing. So this helps us not have to go about defining every single symbol we use. And this is great when you're trying to get into your environment and just start working on your homework right away. For example, we'll talk about the equal signs now. When you say something is equal to something, you're projecting an equality. But this is for a variable assignment whenever you use a programming language. If you try to use the logic version of equals, the 2 equal signs, this is used to determine if 2 objects are the same both in structure, type, value, etc. So we'll try a very, very simple experiment. We'll just say x plus 1 is equal to 4. And this is the logic operator. It's going to return false, as you'd expect. We haven't defined x, so there's no possible way we could know. But it turns out that there's some even worse applications for this. Let's take, for example, this equation. If you multiply x minus 1 and x plus 1, you're going to get x squared minus 1. One problem with SymPy is that for things to be decided to be equal by a logical operator, they have to have the same structure. They can't only have the same value and data type. So something that you might not expect is that when you compare these two, it's going to pop out false. And so hopefully you don't think there's no way to solve this, go around this, but there's a very simple solution. We simplify f minus g. If f is equal to g, obviously this is going to pop out 0. And this is a very easy way to, whoa. Well, it still popped out the number. That's okay. We'll ignore that for now. It's all good. Yeah, it's who knows. But there's this neat little theorem called Richardson's theorem. And essentially, I'm not going to take you here, but it states that we can't prove that every equation is equal to another one that has the same value. So this is especially bad when you use irrational numbers. You can't prove that pi is equal to the sum of some other irrational numbers very often. So the best way to check this at times is to check it numerically. So we say we provide the equals method, and this tests a couple of random numbers for both functions and sees if they're within a specific boundary of each other. So it checks here and it says, yeah, these two are the same function. All these being said, we create equalities by actually using the EQ method. So what we were looking at before is checking if two numbers have the same data structure type, but now we're making a statement. This statement will be used to solve equations. It will be used to plug in numbers, things like that. We don't discuss data types in depth, but we do know from before that we can define a symbol in a specific domain. So we'll do that for now. True. And furthermore, we can actually define simple numbers according to a specific domain, like the rationals. So a big example of this is if you do 2 to the power of this rational, that should pop out the square root of 2, because we've done it exactly instead of numerically. We'll go on to simplifying expressions. The simplify function, it can handle like a ton of stuff. So it's kind of a amalgamation of all the simplify methods. We're not going to go over them all because it's tedious at points, but there are methods to simplify trig functions, there are methods to simplify powers, there are methods to simplify sums. But we'll test the very simple example. We know this identity, cosine squared x plus sine squared x. That syntax, oops. This is going to pop out 1, as expected, right? But then you can take some other types of functions, some that you might not think are defined within the ecosystem that we're working in. This is the gamma function, for example. This is a generalization of a factorial. So for integers, this is just going to be factorial of x minus 2. When we simplify this, it's going to give us x minus 2, x minus 1. But simplification is not very well defined, as we saw earlier. For example, if we tell SymPy to simplify x squared minus 1, some people might see x minus 1, x plus 1 as a simplification of that, but some people might want to use x squared minus 1 because it has less terms. So to supersede this, we use the expand and factor functions. It's very simple. Expand performs an operation, and so it puts it in terms of as many monomial terms as you can. Factor does the opposite, and it guarantees that you have an expression that is irreducible. So we'll look at f is equal to, I've already defined this. Yeah, we'll just say g is equal to factor of f. We'll print the. No. We'll define this. X squared minus 1. We can factor f very simply into x minus 1 and x plus 1. And then we can similarly expand g very simply. But one thing we can check is that the expansion of g is equal to our original method f. And so that's true. So you can get the exact expressions that you want and qualify statements way easier when you've simplified them by the method you've chosen. So for example, there's trig simplification, there's power simplification. If you pass simplify, the algorithm might not decide that those are the best ways to represent your function. So we'll start with something else. X plus 1 x minus 2 minus x times x minus 1. And we'll factor f, or we'll expand it actually. So the weird thing about expand is that this is the most reducible amount of monomial terms that we have. So expand will simplify things at times. It only depends on what basis you're going on. So furthermore, we'll define another function here. Take factor x squared times z plus 4 times x times y times z plus 4. So this one's a big one. We'll factor this out. We'll get z x plus 2y squared. This example is useful to test this other function we have. It's called factor list. Factor list will tell you all of your factors and to what power they're applied. It will of course return 1 because every number is divisible by 1, but then it will tell you, oh, this is divisible by z 1 time, the multiplicity is 1, and it's divisible by x plus 2y 2 times, the multiplicity is 2. Furthermore, oh, I don't want to do this one. This one's long. Plus x minus 3 plus 2 times x squared minus z times x squared plus x to the third. Print out this expression to use it with our collect function. Our collect function will simply take out the term that you want, and it'll put it out to represent this function in terms of a specific factor. So let's take collect expression, and we'll factor it in terms of x. It'll just take out the x of every equation, and it will give you the coefficient with regards to x. We can use this in tandem with another function very efficiently, or coefficients x, comma 2. The dot coefficient function will search for your x, the power of your x, and then it will tell you what the coefficient for that specific term is. So for example, for our x squared, we have 2 minus z. These two in tandem make it very easy to find a factor or a specific coefficient for something that might be a sum over n is equal to 100. And there will be times where this is probably the most efficient thing you can do. We'll delete this cell. Cancel, we'll just put an expression in terms of a rational. So we'll take f is equal to 1 over x plus 3 times x over 2 minus 2 divided by x minus 4. We'll print out this x. A very complicated function that you wouldn't take your time to actually get the greatest common denominator or factor out. But with cancel, we can put this in probably the simplest form you can find this. We have another function, a part. This performs partial fraction decomposition. This might be useful to pass when you do an integral specifically, because some integral methods are limited by the algorithms, and there are ways where your integral will go the other way. It'll use another algorithm to solve it when it could have done it with partial fraction decomposition. So we'll take huge. Take 4 times x to the third plus 21 times x to the second plus 10 times x plus 12 to the 4 plus 5 times x to the third plus print this out. And we'll just do part expression. And it'll put it in terms of a factorization of partial fractions. So we'll see how we can use all of these functions to simplify about as huge a term as we can. This function that we're defining here, we're defining a function based on L. It's a bit complicated, so I won't go over the specifics, but essentially it adds every term that you pass it as input. So it'll do this as a fraction, and it'll do a sort of periodic fraction or an infinite fraction, depending on how you approximate it or to how many terms you do it. Over here, we can define symbols en masse. We can do A0 through 4, and we can pass this to the list of fraction, which is our function from before. And this way, we can decipher what a periodic fraction over n terms would look like. Furthermore, we can use the cancel function to get a really good expression for it. So this is probably the premier way to pass it onto a numerical solver, for example. SymPy does go further in this example. So we'll get to calculus now. There's a bunch of functions in calculus, but they're all very simple. You pass the bounds, you pass the function, and you pass the variable with which regards to you do your calculation. So here we'll define A is equal to symbols A. F is equal to goodness. This function is specific. You pass the function. So in our case, let's do A times sine of x over x. Yeah, we'll do it with regards to x, and we'll say that it approaches 0, and we'll say that it approaches 0 from both sides, so plus minus. If you choose minus, it'll approach from the left, and if you choose plus, it'll approach from the right. So we'll do this, and we'll print out our f. This is how our limit looks like. And if we do the f.doit function, we can just perform this calculation, and it turns out, as this approaches 0, sine of x over x is equal to 1, so a times that is going to equal to a. We can actually even take an expression, a piecewise function, sine of x is above 0, sine of x is less than 0. We define the bounds on which this function is held, and we can print this out to see what it looks like. Essentially, it's sine of x for any number above 0, and it's cosine of x for any number below 0. We don't define 0 just to show a special case in a little bit. So we'll do the limit as expression of x approaches 0, and we'll do it from the positive side. And it will equal to 0, as you expect. And we'll just copy and paste this, and we'll do it from the negative side to see what it looks like. And it will give you 1, as you expect. When sine approaches 0, it gets to be 0. When cosine approaches 0, it gets to be 1. Now, we'll do the limit here, but then we'll do it from both sides. And maybe as you'd expect, it gives you a value error because it's not a valid limit that we can get to. There's not a lot of times where SymPy will provide you an NaN function, so it's best to avoid ever getting that result to begin with. We'll now look at the diff function. You can define this a couple of ways, but you can define the object that's unevaluated by derivatives. There we go. And we'll do x squared comma x printing. There we go. And it puts the derivative out there. But if you want to evaluate, you do g.doit. And it will give you the derivative pretty simply. We can also do this with regards to multiple variables. So we'll do x squared times y, print this f, and we can do diff f comma x. We can do the same thing for y. We can do it for x and then x again, which will give you 2y. We can do it for y and do it twice by passing 2, and it'll give you 0, of course. And it goes as far as your mind desires. You can go diff y2, x2, and it will of course go to 0. Let's go to the next page. Furthermore, you can actually do this with regards to n. You can do n derivatives, but it doesn't always go well. So we'll try this first. And it will give you a very tough expression. Now, we won't look at that because that's SymPy kind of just doing its thing. But there are some expressions where it's very valuable to actually look at their nth derivatives. So we'll define a bunch of symbols. X a times x plus b to the power of m. And then we'll print out this expression. And then we can do the derivative with regards to n pretty simply. Just plug in x comma n. And if we want to do it, we pass this again, we press dot do it, and it turns out, or actually I'll choose a better case. We'll sub in a value for n, subs n comma 2. Turns out to give you a very good value. And so you can choose any n that you'd like, and you can do this for an arbitrary number. It's a very quick way to get the nth derivative of something. So we'll look finally at integrals. Integrals are probably the jankiest sort of functions you can get. There's almost no solutions to half of them that you can think of right now, and then there's the 90% that you can't think of. So these often have to be realistic cases. So we look at cosine of x. This one is a pretty simple integral. We can press integral dot do it. Oops. Define this as f. Say f dot do it, and it'll give you sine of x as you'd expect. Furthermore, you can pass bounds to the integral, of course, so you can plug in some numbers. And this is pretty important when you get integrals that don't have any meaning until you apply bounds to them, for example, the error function. So we'll do 0 to pi cosine of x, and then we'll do dot do it. We can do another example. This is very similar to what we showed off in the first demo, integral of x negative x squared minus y squared. We can do double integrals, triple integrals, as many as you'd like, as long as you pass in the right bounds. So this is how you write infinity, the module. And then we'll write the same thing for y, negative infinity, positive infinity. Simple object is not callable. Integral x. Oh, it's because I'm out. All good, all good. We'll do this integral. We'll print it out, and then we'll do the dot do it function. We can do it with regards to two variables very quickly, and it'll display pi like it's nothing. So let's take maybe something a bit more complicated, an integral that you would never do in your life, unless you're a little psycho. We'll do x to x with regards to x. Integrals like this that you can't solve, when you plug in the dot do it function, it's just going to return back the integral. So this is, should be f. This. No. There you go. It'll plug back the integral right back at you. This means that the solver isn't sophisticated enough to solve your integral. Or it might just be that it has no analytical solution. So we'll do another sort of interesting integral to kind of show off why it's important to define your variables right. So we'll do this g. We'll do the integral from 0 to infinity of x to the y e to the negative x. If you tell SymPy to do this, it'll give you two different answers. It depends on what the domain of your function is. So for y is above 1 and for a real y, it'll give you the gamma function, which, as we said before, is just kind of like the factorial. And for otherwise, it'll actually have no solution. So what we'll do now is we'll define our symbol for y again. But now we'll say this y is actually real. He's not a fake one. And then positive is equal to true. We'll take this function right again. And then we'll say, do it now. And sure enough, it'll plug back the domain for the real y. Another thing you can do in SymPy, this might be useful if you want to truncate an integral that you can't actually do analytically, is you can do a series expansion of it. So we'll take f is equal to sine of x, and then we'll do f series, the variable being x, and then the point by which you do the expansion being 0, and the amount of terms being 6. And it will give you the Taylor expansion for this. In this case, this is the Maclaurin expansion, and you can do it to arbitrary number of terms, although I don't see why you would want to. But this is very useful if you can't find an analytical solution and you want to give an approximate value for this. As long as you know that your function declines as it goes to a higher value. So if you're on a domain from 0 to 1, x to the third is only going to be, it's always going to be way smaller than x, for example. So we will, this over here that we're looking at, it just tells you the next highest term that we took away from the series. So what we can do is we can do operations on this O. We'll take O1 here and we'll multiply it by x squared. And sure enough, the term that we're missing now is our x squared. Furthermore, you can actually do the series as we did before. You can just remove the O term. This is just for aesthetic, I guess. That object is, oh, there we go. We'll skip over this differentiate finite function. On the docs online, you can find out what this does, but it's kind of useless unless you've gone into numerical analysis. It just kind of gives you finite differences, approximations for derivatives. But we'll look at some examples now. We'll define a few variables, and we'll take some fun little limits, integrals, etc. This limit over here, I recognized this just yesterday. I just found this out. Anybody have any idea what this limit goes to? Brandon? You suck, man. Why the heck? Guess right. You're supposed to guess wrong, buddy. We'll do the derivative. We'll do some complicated derivatives now. Pretty much anything to the power of anything is going to be a little crazy, but SymPy does it with no issue because derivatives are one of the few things you can solve for really, really well. Pretty much the only things you can't derive are things that are not elementary functions in any single way. We'll do another complicated derivative here. Anything to the power of anything is tough, but the computer does it without problem. Here we're actually going to do a problem from the Putnam exam. Does anybody know what that is? All right, so the Putnam exam, there you go, buddy. It's probably the toughest exam a math undergraduate can take. The average score is from 0 to 5 out of 120, and the only people who take this are people who are in math. So you can tell this is kind of a killer test. But it turns out one of these integrals from the 1985 test, problem B5, which is one of the hardest ones, you can do it with Python very simply. And it kind of speaks to the power of the package that we're looking at. We'll now look at solving equations. So we'll define x is equal to symbols, x, once again, f, why do I keep doing this? F is equal to equation, x squared, comma 2. And print f. This is how we said earlier that we define equalities. Equalities are useful for solving both sides, and to solve an equality is a little different from just doing an integral. So there's a couple of functions to do this, or a lot of them varying in specificity, but the broadest one that gives very nice results is solve set. So we'll solve this equation, and it will give us every single solution. X squared is equal to 2 gives us x is equal to -2. Or negative square root of 2 and square root of 2. But there's a way to actually solve these without using the equality object, and it's kind of a simple little cheat. We take this x squared is equal to 2, and we make it x squared minus 2 is equal to 0. Solve set, by default, assumes that one of your equality sides is 0 if you don't pass an argument to it. So this is going to give us, or let me see, go with F. This is going to give us the same answer. Furthermore, it can solve for entire domains or ranges of numbers. So something that's a little silly is to say, let's solve x minus x is equal to 0 with regards to x, and then we choose any domain that we're interested in. So, for example, the integers. For integers was not installed. Oh, it's capital. And the result will, of course, be every single value of x that is an integer is a solution to this equation. Furthermore, it can solve for infinite sets. For example, sine of x minus 1 is equal to 0. We'll solve for x, and we'll solve in the domain of real numbers. And this will give you infinite solutions, of course, but SymPy can still be smart enough to sort of tell you and guide you where you're at. We'll solve also some impossible to solve equations. For example, exponential of x is equal to 0. And of course, the solution will be the empty set. So that means there are no solutions at all. Let's delete this cell. We can use the solve function pretty similarly, but the solve function is a better shortcut for doing multivariate solutions. So we'll define f is equal to x squared plus y times exp z. We'll print out f. We can do xs is equal to solve f comma x. It out, and it will give you the solutions. And you can do this with regards to any parameter you want ever. So for example, we can do it with regards to y. And this is very useful when you want to get a general solution, and then you want to plug in a number like, say, x1, and we'll do the array, pass an array, z, comma 2. Let's see, dot subs. Oh wow, wait, where is that? Oh, right, there are two solutions here, so we got to select one of them to actually sub into. And we'll see from this, let's comment this out to see what the function was. First solution was negative x squared e to the negative z, and with subs we can very simply get an exact expression for this. So we'll skip a lot of these little minute details. We'll go to linsolve. This is probably, if you're a CS major, engineering major, this is probably your field at the moment. We're going to solve systems of linear equations. So this is essentially some linear algebra that we'll go over later, but is useful to get out of the way. 2 times z minus 3. We'll plant this f, and we have a system of two equations. Function linsolve will solve for all equations and simplify them as much as possible. So in this case, we have 3 unknowns, but we have 2 equations. So obviously, we're going to get this in terms of one variable. So we'll solve this for x, y, and z, and we'll get this in terms of y. And it's easy enough to choose one of these and plug in your subs again if you want to solve it. But it's always great to reduce your expression as much as possible. We can do linsolve with matrices as well. So we'll do matrix. We'll do 1, 1, 1. When you define a matrix, you're defining it row by row. So we define the first row. We apply a comma. We define the second row like so. And we print the matrix. It'll give you this nice little square matrix. We can print, or we can make another matrix to perform operations on. So we'll do matrix 3. let's display this one. And we'll see that it's 1, 3. So our point now is to apply linsolve to solve it in terms of AX is equal to B. That's essentially what we're doing whenever we're solving one of these systems of equations. So we can do it with the augmented matrix form. And essentially what we do is we stitch this 1, 3 to be the fourth column for this matrix. And that's now the augmented matrix. So we'll do a new matrix here. This one is kind of big. Do 1, 1, 1, 1, 1, 2, 3. And then we'll do with regards to x, y, z. And it will solve it just like so, like it did before. This is probably more useful if you have a ton of equations with more complicated variables. So for now, something simple like this is probably better fit to defining a function with an array. There's another way to do it, and you can check it in the doc that we have, but it's a bit redundant, so we won't go over it. What's a bit more important is the nonlinear solve function. This solves systems of nonlinear equations, which you have to find a decent system to test this on because it's very hard to find solutions for systems of nonlinear equations, specifically analytically. There are various algorithms to do this numerically. So we'll print out this system. We can print out our variables as an array. First is equal to x, y. And we can do nonlin solve system. And it'll give you a very complicated solution, but this is better than you can hope for most of the time. One thing to mention is that if we solve something using solve set, say something simple, x plus 1 for x, it'll display your solution, but another way to do it is to use roots x plus 1. And it'll display your solution and then your multiplicity. So we have an exact multiplicity of 1, which means there's only one time where the solution to this is -1. Finally, for solutions or solvers, we'll use dsolve to solve some differential equations. This is probably the most iffy method that SymPy has. You have to be very specific with what you pass to it, and you have to try a lot of things until something actually gives. But we'll look at an example you might look at in your differential equations class. It can do those just fine. X, f, x, sine of x, if q. We'll define another cell here. Besides defining symbols, we can actually define functions as well. So we'll do that right here. It's better to be specific about your data types whenever you work with them. So let's say this is a class equal to function. And we can print out f of x just to see what it looks like, but it's not too exciting. But we can solve this differential equation pretty simply. We print it out here, and we simply use the dsolve module. We plug in our differential equation, and then we plug in the variable with regards to it. So in this case, our variable is not x, but f of x. We're going to solve it right here, and it'll give us a general solution. You can pass in initial conditions, boundary conditions, etc., but they're very iffy, and as such, I don't want to show them off too much in case they get an error. But we'll go to the next section now, matrices and linear algebra. We can make a matrix object as seen before with the matrix method. So we'll do one right here. We'll do 1, 2, 3, and then we'll do 3, 2, 1. We can print out this M. If you make a matrix with a single row or column, it's going to default to a vertical matrix. We'll see here. Print out this N. But there's a ton of methods we can apply besides simple operations. So whenever you pass on this multiplication, you're performing matrix multiplication, not an array multiplication like a MATLAB might do if you pass in the dot multiplication, for example. So we multiply two matrices. The output is going to be a 2 by 1. We can also get the shape, specific matrix, by just passing in shape. We can specify a row. So for example, the index 0 is where it starts. So here we check the first row of our matrix, and this does happen to be true. And then we can go for the column as well. And we can start from -1, which means take the last column of this matrix. And it does happen to be 3, 1. Furthermore, we have a couple of methods we can apply. The most important being column delete. This deletes the column, whichever one you specify. And what's a little bit shady about this is that this modifies the variable in place. So whenever you call this, your m is going to change permanently. You don't have to define it again. However, there's also a method called m.rowInsert. This doesn't do what was done before. It doesn't change the matrix unless you define it again. We'll add in the row 0, 4. Print m again. This doesn't change the matrix in place. That's generally very bad syntax. I'm not entirely sure why they make it so that call delete changes your matrix permanently, but there are ways to kind of get around that. Particularly, you can just insert the row again whenever you want. So we'll look at some other operations we can perform on matrices. So is equal to matrix. We'll find another one here. And we'll find another matrix here. We can do simple operations like summing. We can show off addition again. More importantly, we can show off matrix inverses. So this matrix M has a definite inverse, but the problem with N is you'll look here, it only has one linearly independent vector. So if you try to get the inverse of N, it'll pop out an error. Just never try to get things wrong is kind of the point. But we can do some other operations like the transpose, pretty simple. Here we go. And we can take the determinant by just passing determinant. So we'll skip a few operations like reducing to row echelon form, null space, column space, but those are all totally available in the documentation. More importantly, we can get the eigenvalues very simply. So it'll tell you the eigenvalue and the multiplicity. And furthermore, if you actually check for the eigenvectors, it'll give you the same info. It'll run a bit slower by default. It'll give you the same info, so the eigenvalue, the multiplicity, and it'll also give you the eigenvector for this matrix. We'll skip a few methods as well, primarily diagonalizing, if you want to look at the doctrine of that. And then getting the exact lambda values or the eigenvalues for the equation. Well, we'll do a little demo now. Some applications are good. I made this beautiful image on Paint. You might be able to notice if you look really closely. But the equations for this are we go over each loop and we count the voltage differences for each component. So this comes out to these two equations. We can define them very quickly, and we can solve them by defining our system of equations and the variables that we care about, in this case our i's, and we can do our nonlinear solve. And we can see here that it depends on at least 2 v values and at least 3 r values. So we can sub this very quickly to get a very simple solution to our I values. In this case, I just plugged in some random resistances and a couple of random potential differences. Here's an example I made for a friend. He knows who he is right now. He's looking at me, in love with me, I think. we will solve this big statics problem. There's 3 reaction forces. Don't ask me what that is, but there's about 10 forces, 1 in X and 1 in Y for each pivot around this statics problem. We have 3 applied forces, and then we're going to have 7 different tensions. So we have 10 unknowns, and then we have 10 unknowns, and then we have 10 equations. So we can put this into a matrix. It's not pretty, but we can do it. And we can define variables en masse and solve this pretty quickly. So here's our A, here's our X, which is what we're solving for, and here's our B. We're doing our AX is equal to B algorithm again. So there's a bunch of them here. We can define them over here. When we do this colon, we go from 1 to 3, not 1 to 4. It's a little counterintuitive, but what are you going to do? We define our matrix, a bunch of values. Let's print this guy out. Sometimes it doesn't run, but thank God it did. And then we can print out our variables of interest. We can do our lin solve to solve for all of them. Do you think this will work, Brandon? Yeah. Well, yeah. You can't even see this because it's on dark mode. Let me do something a little iffy for a bit. We'll change this to light mode. I know, it's a shame. We'll change this to light mode. We'll go back to our output. Our output is here. It's simply too big for SymPy to want to display it. It's telling us, like, please stop, don't do this to me, buddy. But we can plug in some solutions and get something that fits in our window. So here I'm just plugging in 10 for every force in X and Y. And it turns out we can get a solution for every single variable. Now they're not very simplified. So what we're going to do is we're going to apply this eval-f method. And this solves for things exactly. It'll apply every square root of 3. It'll do every sum. It'll do every negative. It'll do pretty much everything. It's like plugging it into a calculator. We do this for the range of all the variables, and we print it, and we can get all of them very quickly. So that's our cute little demo. Did you like it, Chris? Thanks, man. We'll go on next to numerical analysis and typesetting. This is the cool section. The rest of them were a bit iffy, but we get to plot some things now. Let's say our expression is, sine of x, something simple like this. We'll print it again, just in case, and it gets the sine of x. The lambdify function turns this into an actual function in Python. So you can choose which package you want to do this with. But for example, we can choose x. So this is the variable that we get to change in our function or expression. And then we choose NumPy as our natural package to go with this. And we'll say this is f. We'll print f, and it'll just tell us this is a function. We've turned it away from being symbolic. So if we plug in f is equal to 0, sine of 0 is of course 0. If we pass a list to this, 0, 2, 3, 5, it'll give you an output for each single element you put in. And now we're going to use one of the packages that we imported a long time ago to make an array. This array will go from 0 to 2 times np.pi, and we'll do 1,000 points. So we're creating an array from 0 to 2 pi. We're doing it discretely, and we're taking the same interval between each point. Let's see. So there's this function matplotlib inline, and then we'll simply plot this with a package we defined before. We'll do x, and then we'll do f of x. And then we'll do plt.show, which shows us our new plot. Line magic, oh my goodness. Okay, this is okay, no worries. Okay, printed it out outside, that's all good. But we can get our figure here, and we can tell that looks exactly like a sine function. It does it pretty well and exactly. So next, We'll skip another expression to do this cute little demo. We can plot functions of two variables, and there are a couple of ways to do this. You can either do a heat map, or you can do a 3D plot where it takes in like x and y and gives you a z. So here we define our array as before. We make a figure with this specific size, and we use the np.meshGrid function, which essentially returns the lattice of every single point in the interval that you have. So in this case, this is going to couple -10 to 10 for every x and every y. So there's going to be each array, each one of these is going to be a 250 by 250 array. And when you plot this, it's going to match each of these with its corresponding element in the other array. So here we get our x and y, we define it. We define our function, something like sine of x plus cosine of y, and we lambdify it. Let's remove this again. And we do our plt.colorMesh. We put in a couple of labels and titles, and we can show it pretty quickly. So it will give us another figure, but this is essentially what sine of x plus cosine of y looks like. It's a bit of a funky function when you look at it in 2D, so we're actually going to plot it in 3D now using a similar sort of package. And it'll give us a 3D function. You can change the number of sort of lines that compose this by changing this argument here, or we can rotate it in case you want to do that. It looks a bit freaky because you're kind of looking into it, but you have a big degree of customization when it comes to plotting. The last thing here is typesetting. There's exactly one line for typesetting because it's not a very complicated thing, but we can print here the LaTeX code for each and every single function. This is important because our Jupyter Notebook also kind of runs on LaTeX. So we can make a new cell here and choose Markdown. And if we put, what is this, the $sign? It's the $sign. If we put the $sign here, we put this in math mode and we plug in the values we got before and it'll get our cosine. Anybody here use LaTeX? Okay, Brandon, we get it. But it's very useful when you're trying to get some homework done and just plot out stuff as quickly as possible. Finally, we're going to do our little project. Here is, we're solving the Schrodinger equation in 1 dimension. And then we'll be done. We'll define a bunch of variables. So one thing you can do in Jupyter Notebook is you can press backslash and then something like alpha, for example. Alpha, and then press tab, and it comes up with the actual character. So it's a silly little thing, but it makes my day every time. So we'll do h bar. This is the Schrodinger equation, by the way. It's a partial differential equation in 3 dimensions, where we're going to do it in x, and we're going to do it time independent, so that it's pretty much just an ODE. So an ordinary differential equation with 1 variable. We're going to print out all of these values that we see here. We're going to define objects for them. Deal with the symbols. And this is going to be sort of the bulk of it. Comma v, comma e, comma x. We'll define k and a because this will be useful when we solve our ODE. So we'll say these are positive. A bit important to get this right, otherwise it kind of just goes funky. And then we'll say our n is going to be a symbol. It's going to be an integer. And it's going to be positive, so it's a natural number at this point. We define psi here. It's a function psi. And it's a function of x specifically. And we finally get to define our expression. Our expression here is our quality, negative h bar squared over 2 times m. We're just copying the equation at this point, times psi dot if with regards to x twice plus v times psi. And that equality is going to be equal to e times psi as we see above. We're going to print this out. Name E sinus. Oh, here we go. Why does it do this? It like even prints it out. It's all good. So we define our function. This is how it looks like. We can solve it by solving the ODE that's related to it with dsolve, but we'll get to that after explaining a little bit. We'll treat a specific case we call the infinite quantum well. So the analogy to this is maybe a wall, a perfectly solid object, a rubber wall, and you're throwing a particle in there and it's just bouncing back and forth. So the potential here is 0 inside of this wall from 0 to A and infinity otherwise. So the particle can never be outside of the well. So we never need to solve the equation there. But inside of the well, the potential is as simple as it gets. It's exactly 0. So now we're solving a simpler equation, a simpler version of the Schrodinger equation, where we take away this V term. And we'll plug this in very, very quickly. So yeah, we'll do LHS, the left-hand side, is equal to the equation. What did I define the equation as? Expression. Do expression dot left-hand side. This will return the left-hand side of whatever equality. That object is not callable. Let's see. See, it does this pretty well. This is the left-hand side of it. We'll say dot simplify. Simplify here. And we'll say it's now equal to itself, but we sub in the value of 0 for our V, which makes our equation way simpler to solve and actually possible at this point. There's a lot of ways you can't solve this equation. There's way more ways you can't solve it than you can, which is a bit sad. And then let's say we actually divide this by, okay, this is what we're going to do. We're going to divide our expression here. We're going to divide this by these sort of extraneous values that don't matter to us too much, are h bar squared over 2 times m, just to simplify this. Let's put it over 10 times. Goodness. Let's see. You can do this a little bit better. We'll save this, and then we'll say LHS is equal to this, LHS over the value here, and then we'll do simplify. Squared operand type. Where does this come from? Oh, got it. H bar. There we go. Negative H bar. We'll still say this, but it does solve it. That's all we care about, really. We'll do our right-hand side now. Our right-hand side, we want to plug it in so that we're doing it in terms of an arbitrary variable. So we can solve this a bit simpler because there are some inputs you can put into our differential equation solver where it doesn't actually solve it. So we'll do RHS.subs, and we'll sub in our E with negative K squared, where K is what we define here, square root of 2me over H bar. And we'll print this right-hand side. It'll give us the error again, but who cares? We have our right-hand side, and our expression is now our simplified equation. So expression is equal to EQ LHS, our left-hand side, right-hand side. And now it's looking a bit cleaner. We can solve this with the dsolve very quickly. So we'll say dsolve expression. We'll just print G. And it will solve this and put it in terms of sines and cosines. Now, all we have to do at this point is solve for both of the C values and for our K. So how we'll do this is we'll say define this as our g dot right hand side. This is our printed again. And we have two initial conditions. Essentially, at the point 0, we have our infinite potential. So the wave function, which determines where the particle is, has to be 0 at that point. Similarly, for A, it also has to be 0. So we'll plug in psi of 0 is equal to 0. And this will give us C1 sine of 0 plus C2 cosine of 0. The sine of 0 is obviously 0. So when we solve, when we actually even put this equation into SymPy, and we sub in x is equal to 0, and we say it's equal to 0, it'll just tell us the value of C. Because at this point, we know that from this equation, C2 is equal to 0. We'll do this for the second equation, which is psi of A is equal to 0. It gives you this. So we'll just define this as system2 is equal to equation expression does right hand side dot subs. We'll sub in A for x. And we'll say this equals to 0. We'll print it out just to check. And so we have our two expressions. Let's define a couple of symbols. Let's say it's equal to this. C1. Our system2 is now. We'll define this again so that we can use these free symbols, because otherwise you can never sub them in for anything. We'll say C1 times sine of x times k plus C2 plus cosine of x times k 0. Say this is system2 actually. We'll plot this, or I'll put this out. And we'll sub in some of the values that we found before. So we'll sub in system2.subs. We'll sub in C2. We'll sub in 0 for that, because that's what we found before. And then we'll sub in A for x. Print this out. And we get a way simpler equation. So now we have only one, or we have two at this point. We have our K and we have our C1. We have a couple of more conditions to actually solve this, and we'll show them later. But for now, we can solve this for K, and we can say dot simplify. It says the solution to K is 2 pi n over A, and then the union of that set with 2n plus 1 pi over A. So you might notice 2n is every even number, 2n plus 1 is every odd number. So the actual solution that the computer is saying is that k is equal to n pi over A. So this is what we're going to plug in. K is equal to n pi over A. We'll do solution is equal to system2 dot left-hand side dot subs C2 comma 0, and then we'll plug in for K. K is equal to n times pi over A. Now we've decreased the variables by 1. We still have our C1 here, but the way we solve for this is we normalize the wave function. So our wave function, we can get the probability from. The probability of a particle being in a specific x spot is going to be the absolute value of our wave function squared. To normalize this, we say, well, the probability, or the sum of the probability everywhere, has to be equal to 1, just as the sum of you getting heads plus tails for any given throw is also equal to 1. And we'll solve this integral to get our C value here. We'll take only the positive solutions to make it simpler. So we'll say C1 squared is equal to this value. So we'll say that is equal to integral subs. We'll sub in, or we'll solve this for the bounds x is equal to 0 and x is equal to a. We'll say, do it now. And then we'll say, simplify it. And finally, we'll sub in 1 for n. It's an attribute subs. Oh. Print this out. And now we found out what our integral here is equal to. It's a over 2. So it's very simple to solve for this at this point. Let's say this is the norm. We'll solve c1 squared minus a over 2 is equal to 1 over FAC. Wait. Let me restate this. Norm is equal to equation. We'll do c1 squared. And that's equal to 1 over our integral that we found before. We'll say norm is equal to solve norm. Let's see if this prints out the right thing. Nope. We're solving for c1. So yeah, we have our two solutions here. We're going to pick our positive one. So we'll say norm is equal to solve 0, 1, which picks the second solution. This will be square root of 2 over square root of a. And we're nearly done. We now have our equation. Psi n is equal to our equality for psi. We sub in our solution, c1, comma FAC, or common norm. We'll sub in our norm that we just defined for c1. And this should be the final solution to our equation. It'll do the thing again, but we'll see. Oh, psi of x has now been solved for all of the possible variables. We now have our n values, which are arbitrary. We can pick any specific eigenfunction here, and our a is something we define by ourselves. The last thing we'll do is we'll plot this just to see kind of what it looks like. Psi n dot right-hand side. We'll say sol f is equal to lambda phi n comma x comma a. That's sol. And we can plug in a few simple numbers. 1, 0.5, and 1, just to see if it works. Well, it surely does, even though it's a bit deprecated. But we'll now do our last thing, which is to print what our actual function looks like. So we'll say, let's create this linear space from 0 to 1. We're going to say our a is equal to 1. We're going to do 1,000 points. And then we're going to do, let's print a couple of them at once. For I in range 1, 5. So this will take I is 1, 2, 3, and 4. We'll plot our solution of f I, so the n values over here. We'll print our x values, which is r, and then we'll say a is equal to 1. And we'll say the label is something like n is equal to this, and we format the n value here. Do a legend, or do plt.show label. Let's see what comes up in Brandon's computer, if it does. Not this, not this, this. There we go. So now here we've plotted our solutions for n is equal to 1, n is equal to 2, n is equal to 3, and n is equal to 4. If we want to find out now the probability of this particle being anywhere specifically, we can say plot the probability density as with regards to x. So we'll say R. We'll do the absolute value of our sol f. We'll do n is equal to 1. R 1. Absolute value squared of this. And we'll do plt.show. And finally, we can get the, oh, it's plotting it on top of the same thing. Let's say, plot this specifically, and this is the probability density for our particle that we're looking at in this bounded well. You'll see that the area of this is approximately 1, and you'll see that the particle is most likely to be at the very middle of the well. But we can do this for different n values. It might be more interesting this way. For example, for n is equal to 3, you'll see that there are 3 spots where the particle can be very, very probable to be at. We can do this with an arbitrary number of spots. And you can sort of generalize this and see that at n is equal to infinity, it's about as likely to be everywhere as possible. So it's a totally flat probability distribution. And that's about it. We've gone over pretty much every single thing in the modules that we have. All of this is online on the sheet that we provided. Sorry if it was a bit hard to follow, but at the very least, you'll be able to look at the reference and be like, oh, I get this, I think. But yeah, that's all. Thank you.